And now please welcome to Max Butler, and who's going to talk about simulation-free path-based inference for stochastic differential equations. Is it recording?
Should be recording.
Okay, hello. This is mostly my MSc project, but I've done some additional work on trying to understand the limitations and stuff like that that I can include in the end compared to my presentation for those of you who were there earlier, a couple of months ago. So SDEs are important in many fields for modeling things. They allow practitioners to capture both the things they know and they understand, maybe some physics that they understand about the system, but then also the things that they either don't understand or they can't hope to measure. They can include them in the stochastic component. So, for example, with weather, you may know what's happening from a physics standpoint between all these particle interactions, but you can't hope to possibly measure all the different particle interactions that could be occurring. And then in option pricing, you might understand some things have some relation to the price, but there's so many unknown things that can happen that you can't possibly predict or even understand how it impacts the stock price. So you can have an amazing model, but you also need to fit the model to observations. Now, if you have something nice, say an OU process, you can use the closed form transition density, and you can just do an MLE, you can embed some kind of prior, go Bayesian, but you have a lot of options, and you know they're going to work well. However, if you have something more complicated, something quite nonlinear, then you're unlikely to have an actual solution for the closed form, and then you have to use other approaches to actually fit your models. So you have simulation-based methods, is where you're going to simulate and then compare all the simulated paths you've done with your model prediction against what you actually see in your data. So ABC, approximate Bayesian computation, you can do this and you have some summary statistic that you're going to compare against. You can have augmented data methods where you're going to use a method which works well if your data is extremely fine or other things like that, and then you can augment with some simulation to then allow you to use one of these other methods. And then you have simulation-free methods, which are great because they can be very quick. You can use gradient descent algorithms instead of having to sort of converge on a solution as you would with simulation-based, or if you're simulating Fokker-Planck. But in these, they're not often inaccurate because you don't have the closed form transition density. You can't just use that in gradient descent. You have to either approximate with Euler-Maruyama, assume it's normal, and that additionally the drift and the diffusion of the normal, the mean, and what have you, is just a small increment of the function at your current position times dt, which again is inaccurate. And there are methods that build on this, but there's no method that is going to capture the full law of the distribution and can be made arbitrarily accurate. So in this presentation, we have a novel method which hopefully will achieve that. It's not a free lunch, it doesn't achieve everything, but it is able to, in theory, have the full law of the distribution, and it doesn't use simulations, so it can be quick. And it allows you to do multiple dimensions, though the scaling in the dimensions is not currently clear. So just to understand how this method comes about, it uses reproducing kernel Hilbert spaces. So I don't know if anyone's familiar with the MMD metric using the Gaussian kernel, but it's very similar to that. But the properties that are needed is, if H is a RHKS, it's a Hilbert space. It contains, within that Hilbert space of functions, the kernel function is in that, it's one of the functions, and it also has the reproducing property, as you can see there. So you can use the function, the actual kernel function to sort of recover your function. And for this work, I use the RBF kernel, or the Gaussian covariance function for my RHKS. So the main point of the idea is essentially moment matching. If you want to match one moment, you can do so if you know the expectation of these two things. So you have some distribution xt, you have some model distribution xt tilde, and you want to see whether or not they are comparable in one specific moment with some function h. And you can just easily compare them in this case. However, if you're just going to be trying to calculate some model just using one moment, it's not going to be very good. It's going to be quite poor. However, what if you could look at all of these h's, you had a bag of h's, and you found the one which was the biggest, and then you were to minimize that. Then if that was 0, you would know everything else in your bag would also have to be 0 if you were taking the absolute value, or if you included minus h in your bag as well for every h. And that is essentially what we do. You look at h as coming from a Hilbert space. You look at h as coming from a Hilbert space, and therefore you are drawing all of the functions from that Hilbert space, and to see which one of those is sort of the most discrepant moment. And that's the one you're going to aim to minimize. So what the equation is essentially is the maximum across that thing that we had earlier. And the way to actually get this in the closed form expression is you can use Ries's representation theorem to essentially say that as we have a function that's a linear in h, it's a linear function of h, there is a representer that exists in our Hilbert space such that h, we can take any function h, do the inner product with our representer, and then we get this, we recover our EH_xt, h, EH_x tilde t. So now, using that, we can use the reproducing property to find what the form is of our representer, as we can just take the function h to be our kernel with opening one argument. Then, using that, we can take the norm of our representer to find what the maximum it can be is if we restrict to the unit form by looking at the norm. And as we know the form now of our representer, we're able to calculate this inner product and recover the form of our representer, which is, this here is the form of our representer in such a way that when we take an empirical summation, we will recover this thing under expectation. So just to explain what we have here is we essentially have the expectation of applied to the kernel of our function on the left argument, and then in the middle we have 2 times, so you can see it takes the form of an inner product, 2 times the expectation, and now the expectation is only being applied in one argument, whereas the other argument is left open for data to be put in, and then the next one is a summation across the data that we see, with one argument left open to put the data in. So then when we take a summation across all of these, it essentially ends up being the theoretical expectation on the left, half empirical, half theoretical, and on the right, it's all based off what we see in the data. Now, how do we calculate the expectation? Well, if we don't have a closed form, if it's not as simple, it's not so easy, and apologies for the order of the slides, but we can do a Taylor expansion in time to approximate this moment and assume we have roughly fine data. We don't need too many terms to be able to approximate this moment. So in the rest of the work, and you can see in this plot sort of how the accuracy is as we increase the number of terms that we go up to, that the expectation when we're actually calculating it, we're using a Taylor expansion to actually predict what that moment is. So we now have, there's some method that can say, if we have an xt and we have some x tilde t, and we're using a model for our x tilde t to sort of say how that is, now we can fit that model, but that doesn't really help us if we have lots of sequential observations. We have, say, a sample path of some SDE model that we want to fit. Well, this is not clear necessarily how we can use this to actually have a look at that path in one go. So as the SDEs that I've considered here are all Markov, we can consider them as just sections in a row. So you have your xti and your xti plus 1, and these are essentially multiple settings of an xt and an xt tilde, except we only have one observation of our xt. So what our aim is here is now we have lots of these sort of GINs, except we only have one xi, which is the one we observe in our path. And then we just have lots of that situation put next to each other in a row. And every time we know how to predict our moment because we have our current position, we have our model for SDE and how that works based on our current position in both spatially and in time. So what our aim now is we want to combine all of these observations in such a way that we're not favoring any particular part of the path. So we want to calculate the variance of our GN, assuming that we're correct about our current parameters. So we do a variance correction, and then we sum across all of the paths, variance corrected, and add them all up. So we're taking the empirical average across the path. And then if we have the correct parameters, that should be minimizing this quantity, which is this maximum discrepant moment. And then we should have the best set of parameters for our path. We do have a problem, and that's that at the end of the statement, there was what will end up is a summation across all the other data, or will end up being a double summation if you had lots of data to sum across. But we can't do this because it doesn't make sense if you only have one piece of data. You can't really look at one piece of data and hope to calculate what this is. Thankfully, you don't need to do it, because this function here, if you think of expectation, is sort of in terms of your parameters, because that's your model prediction for the moment. It's not in terms of that. So it's not in terms of any of your parameters, and you're trying to minimize this statement. So you can minimize it without having to even calculate this endpoint. Now, you do need it to make sure the whole thing is mean zero, to allow us to do the variance correction, which is very important, because say you had something like geometric Brownian motion, that can become very volatile at the top. And then what would end up happening is that you'd just be fitting to the parts of the data which had the most volatility. And you would be ignoring the data where it was nearer zero, even though you should be weighting them all equally. So you have to correct it. So the way to do this is just to swap it out with the expectation, because that is what it will end up being if you're correct, but then just don't include that in the gradient descent algorithm. So once you find the minimum, you know that your variance corrected properly, but as you're going down, the variance won't matter so much. Now you could ask the question of, is this going to affect your guarantees of convergence? Could you end up with loops and things like that because your variance is changing as you're trying to descend? That could be the case. In my test so far, it's not been a problem just to have the variance adjustment change as you're doing your gradient descent, and then you reach your minimum and you know that you're taking account of the whole path properly. But it's not been a problem, but it's something to look at. Here's some results. So an example first of geometric Brownian motion, where it does have a closed form, so I can check to see whether or not my predictor is accurate. And so for this here, these are the curves of the function to see how it actually looks. And I've got a dotted line showing the minimum. And the minimum, I've only done 3 paths in this particular test. But at the minimum, I intersect with the MLE. So the dotted blue line is the MLE for the observation, and then the dotted black line is the lowest point of the function, which is what's recommended by this method. And they are very close for all of those. And this is with extremely fine data there, I must say, 0.0001. And the reason for that is because the Taylor expansion, due to how it's currently coded, it's pushing higher numbers is very difficult, but this is due to compile time opposed to due to execution time. So this can be corrected, but I'll need to, because I'm using JAX, and I need to actually edit the JAX modules in sort of the JAX code itself, opposed to just being able to use their existing modules to be able to actually have it apply grads to itself in an efficient way that doesn't have super exponential in sort of unnecessary calculations, but then it gets rid of when it compiles, but it just means the compile time can just become too long to be able to run the test. So that's why I've chosen super fine data. But I've also done some tests, which I'll show later, with further with slightly further apart data, and I have done some more tests with even further in a different setting that I will also touch on. Now, this is where it's more interesting when you have the double well potential SDE, which doesn't have a closed form, transition density. And in this case, how do we perform? We don't have the MLE to fall back on to be able to see if we're necessarily good. So I've let the path be very long, and I'm hoping to have converged to the correct parameters with this method. And I've converged quite well to the parameters. It's not exact. Now, whether or not this is because I have some numerical inaccuracy with my prediction, is it because this would be the MLE if I could see the MLE, or is it just some other issue? Yeah, I'm not yet sure about that, but it is quite accurate though. Now, what I've started to look at now is, what about in the idealized case? So take away the error of the Taylor expansion. So if we have a look at this function here, what if we pick the OU process and then we can compute these expectations explicitly? So we have the exact form of what these expectations should be theoretically, opposed to having to use a Taylor expansion and then go from there. And then we don't necessarily know when we're increasing time or we don't want to do other changes, whether or not it's the Taylor expansion at the moment letting us down, or if it's the fundamentals of the method that are letting us down. So I've calculated this exactly, and then I've run many tests on the OU process, done the exact MLE, and also compared it against this method here to see how it compares with 0.01 dt. And the metric I've been looking at is what is the value of the likelihood of the true MLE, and then what is the value of the likelihood of my estimator, and what's the ratio? What's the likelihood ratio? So I would hope, and then here is the histogram of the distribution over 100 paths of the likelihood ratio. So some of them are quite poor with 0.4. Most are grouped around between 0.8, 80% as likely, and just as likely as the MLE for what we're being observed. Now, can this be improved? There is a hyperparameter in the RHKS, and this hyperparameter affects the variance of the function, and it also affects the variance of the covariance function, and that essentially is how many functions are in our ball. So it's the stretching of the RHKS. So as you increase the hyperparameter, more functions sit within the unit ball. And that is good because it means you're more likely to contain all the functions that will be sufficient to characterize the distribution of the SDE you're dealing with. But the downside is, well, the more moments you're looking at, the slower you're going to converge to the true expectation. So therefore, when you're minimizing this quantity of the maximum of h against these moments in these different moments described by the function h, you're not going to be able to get to 0. Maybe you can only get to 0.5. And so then the parameters you've selected perform the best across all these moments, but they don't perform well. And so really, your selection is actually not good at all. So there's a balancing act between you have to have it high enough such that you have the important functions, but if you push it too high, then you're including functions unnecessarily. That is what is now being I'm currently investigating. I don't know how you can necessarily choose this optimal parameter. Numerically, what's the best? But this is the current situation. I will also say that as I reduce dt, I get an improvement. So if I choose dt to be 0.0001, it starts grouping up around the MLE more and more and more. But as I get further and further away from the MLE, not the MLE, the dt gets further and further away from 0, it starts to spread out and become worse and worse and worse. I had one test where I had 0.01 was the similarity, and my dt was 1. So not an ideal showing. Mu was still good. It was sigma that became poor. Now, is this hopefully this can be rectified with a correct tuning of the hyperparameter. However, how much it matters is unclear, because the real benefit of the method is the fact that you can apply it to complex SDEs and still fit, respecting the full law of the SDE. And if your data is spaced out, even dt equals 1, you're not going to be able to predict with Taylor expansion anymore. So really it only works for high frequency data. So the fact that it becomes more poor, not only because your Taylor expansion becomes more poor, but also something about the method fundamentally might become more poor, maybe does not matter too much. So the conclusion is that there is a novel method that for very high frequency data with complex SDE structures can still provide benefit and allow you to fit in a way that respects the law and is accurate and is very, very close to the MLE. With the downsides being that as you increase dimension, the expansion of the Taylor expansion can become more computationally expensive, so that can be a problem. And for sparsed out data, you also have problems with your Taylor expansion and potentially with the method as well. Further directions is to investigate more the role of this hyperparameter, and is there some analytical way to have an optimal hyperparameter, and can we use this for non-parametric approaches? So instead of parameterizing your SDE and then having set parameters that you're fitting and you're doing a gradient descent against, can you instead use a neural net? Neural SDEs are a decently large field. And what happens if you add in noisy data? Because if you're looking point to point, by disturbing the data, you actually mess with each observation massively. So if you took a weighting, you'd be affected less. If you look at the path zoomed out, you might not even notice the noise. But when you zoom in, which is as the method sees it, point to point, it completely disturbs the SDE and ruins inference. So is there a way to fix this? Because obviously in the real world, you're going to have noisy data from your measurements, or even your data does not respect SDEs on the fine scale. Only zoomed out does it actually act like an SDE. So that could again be a problem. And I would like to, as I said with JAX, actually implement this so I can get efficient compile times to make it more usable for these higher term number of Taylor expansions. Thanks.